representation of the lines PQ and PR. These PQ and PR represent the vectors A and B with the same initial point. If I'm moving from the same initial point P here and here, and I'm going to drop a perpendicular from the point R onto the line A, or the direction A, which is PQ. So when I drop this perpendicular, if at this line, the red line here, which I call it PS, actually will be the vector projection of B onto A. Also here, when I have these two vectors A and B, and I drop a perpendicular from R onto the line PQ, I'll have the projection here, which is برضو PS. So this PS is the vector projection of B onto A. Actually, this notation, we write it like this: projection of B onto A, but these are two vectors. This B is the vector to be projected, and A is the vector to be projected onto along this vector. Now I want to find some formula for this projection. When I say projection of B, this is the notation we're going to use of B along A. Geometrically, this represents, in my figures, represents the line PS, defined by the directed line segment PS, okay? Now, this is a vector. It has both magnitude and direction. If I care about the magnitude, I'll call this the scalar projection of B onto A. Let's draw the figure that represents this again together. If these are my two vectors, this is my vector A. I want to project along two. They're represented by the line segment PQ, and this is the vector B, the vector to be projected onto A, and this will be the perpendicular that I'm going to drop. Notice that this triangle P RS actually is a right angle triangle. By using this right angle triangle PRS, I will notice that the length of the line of interest of the projection, which is PS, but now I'm concerned about the length of this line PS, actually from geometry is equal to P cosine the angle between the two vectors. Okay, if this theta is the angle between my two vectors, then I have the length of this is equal to B times cosine theta. Now recall again, I want to use dot product again here. Recall that when I had the two vectors A dot B, the geometric interpretation or definition was in the product of the length times A cosine theta. Now let's use this in our formula again. But we will notice I could rewrite this like this: magnitude A, okay, and open my brackets, B cosine theta. I'll notice that this B cosine theta actually is the length of my vector PS. So from here, I could say that the length PS could be rewritten in terms of the dot product of the two vectors A dot B, okay, and divided by the magnitude of A. We call this actually A dot B is a scalar, has a scalar result. Magnitude definitely is a scalar, so that's why we're talking about here length. This is the scalar projection, okay? If I only need the length of the projection, I'm only concerned with this component. I call it the scalar projection, or I call it the component of B along A. As a notation, we write it like this: component of the vector B along A. Actually, the formula I arrived at is A dot B over magnitude A. Also, I could look at it like this, as if it's the unit vector along the direction of A, okay, dot the vector B. But whatever, how do I look at it? So what else do I need? Now I got the length of the projection. If I need the projection itself, the PS, now I know that the projection from my figure here, the projection PS is a vector. Let's put the arrow. We need a vector. I need the direction. But this direction definitely is along the direction of A. As long as it's along the direction of A, then the vector P actually will be equal the vector PS will be equal to the magnitude of PS times the direction, the magnitude of PS times the direction along A. If I leave it like this, I will change the magnitude of the projection. So we said previously, here we use unit vectors so as the magnitude does not change of the vector of projection. Okay, now PS from our formula is A dot B. This is the component A part of the projection A of B along A times the vector A over the magnitude A, or it is A dot B on a magnitude A squared, or this is scalar definitely times the vector A. But I could consider it like this: magnitude, okay, times a unit direction, or overall I'm doing the job like this, okay. Let's go take a simple كده example. Example, let's say كده I have two vectors A and B. Let's write كده some specific example. Okay, let's say I want to find the scalar projection, find the scalar projection of, and the vector also, let's find both of them, the scalar projection and the vector projection of the vector B, say given by 1, 1, 2, these are the components of the vector, and onto A, where A is the vector negative 2, 3, and 1, okay. Type, what do we do now? Plus, I know that I have this vector A, and I have a vector B. I'll move them to start from the same point. I know that this will be angle. I won't do anything with the angle. خلاص, I rewrote everything in terms of dot products. So I know that this is the projection I'm looking for. No need to define any points. I'll use the notation. The component of the B. No need to define points. I don't need any actually. So the component of B along A, the formula, let's rewrite it here, A dot B over magnitude A. It is equal to the dot product of these two vectors in front of us, which will be negative 2 times 1 plus 3 times 1. Yeah? This is the dot product between A and B, plus 1 times 2 over the magnitude of A, which is the square root of negative 2 squared plus 3 squared plus 1 squared. That is equal to, these will cancel out, I'll end up with 3 over root 14. Actually, this is the length of the projection of B onto A. Now, what about the vector projection? We denoted the vector projection using this notation, projection of B along A, which is actually the length A dot B over magnitude A times the vector unit vector in the direction of A. I'll get multiplied by A and divide by its length. Let's substitute. Already I computed this value of the length, which is 3 over root 14. The magnitude is 1 over root 14, and the vector A is actually the vector negative 2, 3, and 1. Okay, but this is the finally answer. Let's simplify further with the 3 over 14, negative 2, 3, 1. Or we could also put multiply by the components by the scalar and end up with negative 3 over 7, 3 over 9 over 14, and 3 over 14. Okay, that's it. This is our projection. Actually, it has lots of applications. One of them is finding the work done on an object